Hello and welcome to another ramble. Today we are looking at the department's paper 1 from November 2023, question 9. This is a question for which I had recorded a video, but I messed it up. Not the question this time, thankfully. I messed up the technology. Actually, I don't know what's worse because I did spend like 30 something minutes recording that video only to find the audio was a flop afterwards. So, quang quang quang. But yeah, the biggest downside to all of this is that, I have now seen the question, I've worked through it comprehensively, so there aren't really any more surprises, I think. And I won't be able to, share what confused, well, at least not in real time. I won't be able to share what confused me and things like that. But yeah, I hope it will still be a valuable exercise, working through this question together. And without further ado, let us have a look. So yeah, did I say we're looking at question 9? We are looking at question 9. The text says we're looking at question 9. Question 9, question 9, question 9. The diagram below represents a printed poster. Rectangle ABCD is the part on which the text is printed. Oh, sorry. I think I did yawn when I was recording this video yesterday because I'm not a fan of optimization questions, but again, here we are. The shaded area, so this is this rectangle where the text gets written. It is 432 square centimeters. Right, so the area is 432 square centimeters. Right, and AD is X centimeters. Okay, so this is X centimeters, meaning that this over here will be 432 over X centimeters, right? So if this was 10 centimeters, then this will be 432 over 10. Whatever I need to times this with in order to get an area of 432, that's what the side will be. Okay, so then we're told that ABCD is 4 centimeters from the left and right edges of the page and 3 centimeters from the top and the bottom of the page. First question, show that the total area of the page is given by this function. Okay, so the length, I don't even know what's length and breadth. I guess this is breadth. The breadth of the rectangle is 432 over X, right? So that's this bit over here, plus this 3 and this 3. So plus 3, so that is 432 over X plus 6. Right, and then the length of the rectangle is going to be this bit, which is X, plus this bit, plus that bit. All right, so that is X plus 8. Right, and so the area of the rectangle is going to be the length times the breadth. So the area of the rectangle, technically these are also functions. This is the breadth in terms of X and this is the length in terms of X, but anyway. So it will be 432 over X plus 6 times X plus 8. Okay, so I'm going to expand this. So this will be 432 over X times X plus 8 plus 6 times X plus 8. Right, so if I times this in, we get 432. And then if I times this in, we get a number I've forgotten and I don't feel like working. Okay, I'm going to work it out in my head. So 400 times 8 is 3,200. 32 times 8 is 2 to the 5 times 2 to the 3, which is 2 to the 8, which is 256. So 3,200 and 256 added together gives me 3,456, right, over X. And then on to our next term, we'll get 6X plus a 48. That is not going to fit in, but we will force it. whether it likes to or not. Oh, guys, when did it get flipped? Oh, is it fitting? It kind of fits. Yeah, that's good enough for me, right? And so our only like terms are this guy and this guy, the two constants. So we get 3, 4, 5, 6 over x plus 6x plus, I guess this gives us 480, yeah, which is what we were expecting. So that is the area of the poster in terms of x, right? Cool. So on to the next question. So the question says, determine the value of x such that the total area of the page is a minimum. Okay, so we are going to need to find the first derivative of a, and in order to do that, we're going to first need to rewrite our a in a way that is friendly to our differentiating efforts, right? So this x we need to rewrite as a power of x, right? So that's what it becomes. So a prime will be negative 3, 4, 5, 6 x to the minus 2 plus 6, and we want to see where this is equal to 0. So we are solving this. Where is this equal to 0? So this will be negative 3, 4, 5, 6 x to the minus 2 is equal to 6, x to the minus 2, oh, and this was meant to become a negative 6, sorry. So this will become just 6 over 3, 4, 5, 6, which is the same as 1 over 5, 7, 6, right? And so this is the same as x to the minus 1 raised to the power of 2, and this is also the same as 1 over 24 raised to the power of 2. Yeah, this is not a wise way to do it because it implies that this is equal to this, but actually we would also need to think about the possibility of the negative square root. So this could be 1 over 24 squared, or it could be negative 1 over 24 squared. So actually, like, let me not do it like this because this is muddying the waters. Let me rewrite the equation like this, right? Where it is now clear that, okay, x squared must then be 576. And then we can remember our roots. So x is equal to the positive or the negative square root of 576, which is plus or minus 24. But remember that x is a dimension for this rectangle. So x is some number that is greater than 0, right? Because it is a dimension, right? It's a measurement, it's a length. So therefore x must be 24, right? So that would be the length that optimizes the area of this whole poster. And we can double check that it does in fact give us a local minimum for our graph. We can double check that by figuring out the second derivative, which is so our first derivative is this guy. Just put that somewhere for reference. And I took a 2. Did I take it from somebody? Go away 2. Okay, so our a double prime will be positive 6, 8. Oh, not 6, 8. What is 56 plus 56? 56 plus 56 is 112. So it will be 6, 9, 69112 x to the negative 3, and the constant will fall away. So now if we look at the value of a double prime when x is equal to 24, we see that, well, okay, what do we see? Let's put it into the calculator. So that will be 6912 times 24 to the negative 3. I had messed up some numbers. So when I did this video yesterday, I got some very funky numbers when I put this in. And I think it's because I messed up my sum. Wait, let's just double check. 3, 4, 5, 6. Let's double check on the freaking computer, dude. Okay, so that is 6912. Okay. Right. Anyway, the most important thing being that this is a positive value, meaning that the graph of A is concave up when x is equal to 24, meaning that x is equal to 24 is indeed a local minimum. Right. So yesterday when I was recording the video for this question, I did just become very curious about what this graph looks like in general. And I think when I do an optimization question, I'm always going to kind of add in a little bit at the end where we try and sketch this graph together, which is not a graph that you've learned about, right? It's got a division by x, so that would kind of suggest hyperbola. But there's also like this other x term that's in the mix, which is not really hyperbola. Right? So let's see if we can use what we have learned to try and sketch this graph. And of course, at this point, like, you know, the curriculum is, yeah, we're done with the curriculum bit of this question. So if you are just grinding away over here, you know, trying to finish studying for your June exam or something, yeah, you don't need to stay for this next bit. But if you are just a curious child with time on your hands, then let's do this. So we are trying to sketch the graph of a of x, right? And let me just get our derivatives so that we don't have to keep working them out. Come on. And then our second derivative. Right. Okay, so what do we need in order to sketch our graph? So first, let's talk about, and I'm actually just going to rewrite these as fractions because it's just so much easier to see things like asymptotes. Because, yeah, spoiler alert, there is an asymptote. So this is not just me acting in grand wisdom, this is me, you know, acting from spoiler alert, you know, where I spoiled it for myself. I can't believe my Mabena moves. Anyway, let me exercise some self-compassion, give myself a break. Okay, right. So yeah, I'm just rewriting these as fractions so that it's just easy to see or anticipate certain things. Right. These are so ginormous and they don't need to be. Anyway, so what we need is to figure out our intercepts, okay? And the first thing I wanted to do was to figure out x-intercepts, which is where when this function is equal to 0. So we are solving this equation. Right, and the restriction is that x can't be equal to 0. So let's put everything over x. Okay, so the only way that this can be true is if the top is equal to 0. Right, and of course we could just put this into our quadratic formula, but where's the fun in that? So 6 goes in. I feel like we've already worked this out. I think it's 5, 7, 6, right? Right, and this I'm definitely not in the mood to try and... Am I not in the mood? I do kind of know what the answer ends up being, but anyway, let's just put it into our quadratic formula. So x is equal to minus b plus or minus b squared minus 4ac divided by 2a. Okay. So let's start with our plus. So we end up with x is equal to negative 8, or let's do our minus. X is equal to negative 72. So those give us our two x-intercepts, right? So our x-intercepts are negative 8 and 0 and negative 72 and 0. Right, next up we want our y-intercept. Yeah, should be a y-intercept, not 2. Right, a function is a one-to-many or one-to-one, but never many-to-one. So you can't have two y values corresponding to one x value. Anyway, so all this to say we can't have two y-intercepts, right? Okay, so this is where we figure out what is the value of a of 0. And this is where we see that, oh my goodness, that's actually not defined when x is equal to 0 because we have a division by x. So is not defined. So we therefore have an asymptote when x is equal to 0. Right? Cool. Then next up, we already know, we know a sum of our turning points, right? We found that our turning points occur at x is equal to plus or minus 24. And we already saw that, did we figure out? No, we didn't figure out the value of the function at either of those. So let's do that now. The value of the function when x is negative 24 Okay, so let's put in negative 24 right and see what we get. Yeah. Ah, come on, headphone. Right. Okay, so we get 192, and then if we put in 24, what do we get? $768. Lots of big numbers. Okay, and let's just look at what is the behavior of the graph at x is equal to plus or minus 24, just to determine whether it's a local min or a local max. So we already know that over here it's a local min, right? Because that's what we worked out in the actual question, right? So let's see what's happening to the concavity when x is negative 24. So okay, we can already see that we're going to end up with a negative number, because we have positive and negative number cubed is going to be negative, so we're going to end up with a negative number, right? So that means that our graph is concave down at this point, meaning that this is a local maximum. Okay, right? And do we have a point of inflection? Right, so we are trying to see where our second derivative is equal to 0. Oops. Oh, that's where I'm going to sketch. Okay, so we are solving this, and this has no solutions, right? Because there's nothing you can divide 6912 with to get 0. Like, there are no two numbers that you can times together, and well, there's no number you can times with 0 and get 6912. There's nothing you can times nothing with to get something. So there's no point of inflection. Right, and just to make things very, very clear to ourselves, let's look at where the graph is concave down and where is it concave up. So this guy is negative, or 6912. In order for it to be negative, we will need x cubed to be negative, right? That's the only way that this division is going to give us a negative number. And in order for x cubed to be negative, then x has to be negative, right? So that means that for the whole of this side of the x-axis, our graph is concave down. And by similar reasoning, the only way that this guy is going to be positive is if x cubed is positive, and the only way that x cubed is positive is if x is positive. So for all of this side of the Cartesian plane, our graph is going to be concave up. Right, so let's put all of this together. We have an asymptote where x is equal to 0. Okay, next up, let's draw our x-intercepts. So we've got -8. Well, also let's label our axes, sheaves. Right, so our one x-coordinate is at x-intercept is at -8. The other one is at -72. And then we have no y-intercept, of course. Then we have our turning points. So the one is at -24 and 192. So let's plot that. -24 and 192. I'm going to put it somewhere here. And we know that it is a local maximum, right? Yeah, that's what we figured out here. Okay, so it's gonna be, something like that. And then the other turning point is at 24 and 768. So that's gonna be way up here somewhere. Oh, okay, and it's gonna be a local minimum, so let's not put it too high. So it's gonna be 24 and 768. Also, this is like so in my space. Right. Cool. So we know that this is a local minimum, and yeah, I mean, I'm going to assume that the graph is going to approach the asymptote, and then yeah, there's no change in concavity, so it's just going to do that. And likewise on this side, it's going to approach the asymptote, and then the rest of the time is just going to go further and further up to infinity, because again, it's not changing concavity. And that is that, really. We can confirm these guesses by looking at the behavior of the limits of the function, right? So we want to verify that when x is getting closer and closer to 0, from the positive side, the function is going to go further and further up to positive infinity. So that's the first limit we want to verify. The second limit we want to verify is that when x is getting closer and closer to 0, from the negative side, our graph is going to go plunge further and further down to negative infinity, right? So those are the first two important limits to verify. The other limits we want to verify is what's happening to the graph, or to the function, as x becomes bigger. So as x approaches infinity, is our function in fact also approaching infinity? And likewise on this side, as x is approaching negative infinity, is our function also then approaching negative infinity? So let's quickly double check those limits. So the first one we said we want to check is what is happening to the graph as x approaches 0 from the positive side. Right, and let me just write it out. Right, so let's look at what's happening with each term. So if I make my x very, very small, so 0, and very importantly, positive 0, 0,0000001, what is my function going to output? So first of all, this term is going to explode because I'm dividing 3,456 by a very, very small number. So I'm going to get a very big number as a result, and it's going to be a very big positive number, just to make that very clear, because it's going to be a positive divided by a positive. This term is pretty much going to disappear because 6 times a very, very small number is just going to become very close to 0. The 480 is really immaterial at this point because of how big this number will be. So what this confirms is that yes, as x gets closer and closer to 0 from the positive side, our function is going to just keep going further and further up towards positive infinity. So that confirms our first intuition. The other limit we want to check is what's happening as x is approaching 0 from the negative side. So if I'm making my x closer and closer to 0, but from the negative side, so let's say my x is something like negative 0, 0,0000001, right? So this term is going to become a very negative term, right? Because we're dividing positive by negative, and on top of that, the the thing we're dividing by is very, very small. So that means that this number is going to become a very, 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 very negative number, right? This term, again, is going to pretty much disappear. So you're timesing 6 by something very small. And this term is, again, going to be negligible in the bigger scheme of things, right? So really the most important term is going to be this guy, who is a very negative number, right? When you make x a very small negative number. Okay, no, that's not right. It's not a small negative number. It's because a small negative number is actually more this way. But when you make x something close to 0 from the negative side, right? So that confirms that, yes, the closer x gets to 0 from this side, the more and more negative my function is going to become. Right, let's confirm our limit when x is approaching infinity. So what's happening the bigger I make x? So if I make x a very, very big positive number, 1 million, billion, quadrillion, I don't even know if that's a real number. So I'm dividing this number by that very big number. This is pretty much going to become 0, right? So this term is pretty much going to disappear. This term is going to become very, very big, the bigger I make my x. And the 480, well, potato, potato. The star of the show is really this guy. So the bigger I make my x, also then the bigger my function output is going to become. And similarly, if I make my x very, very negative, right? So if I now make my x negative 1 million, billion, quadrillion, I'm dividing 3,456 by that. Okay, so again, my term is pretty much going to disappear. It's going to be a negative 0,00000. So this term is pretty much going to become immaterial. This term is going to become very negative. So 6 times a million, billion, well, 6 times negative a million, billion, quadrillion is going to become negative 6 million, billion, quadrillion, right? It's going to become a very negative number. The 480 is not gonna really make a difference. So really, this term is telling us that as x approaches negative infinity, which I forgot to update over here, right? As x approaches negative infinity, then this expression is going to become a very negative number, which is also what our graph is showing us, that the function is just going to go further and further and further and further down towards negative infinity. So yeah, those are just some quick checks that we could do to verify that our function is in fact behaving as expected. I would then just also want to confirm honestly that it seems like our function doesn't produce values between 192 and 768, right? It doesn't seem like there are any x values that produce y values in that range. How would we verify this? So let's just see. Let's look at this function again. So it looks like this. And we want to see, are there any outputs that it does not generate? So let me just rewrite this as a fraction. We've done this before. And that'll be 6x squared. Okay, so this is freestyling now. This is not something I tried to do in the previous videos, so it might work, it might not work. Right, so I mean, I can see that this top part is a parabola. And from what we've seen, it's a parabola that is going to do that, something like that. at negative 72, negative 8 is where it would have its x-intercept. Its lowest point will happen at, I don't know, the turning point happens at minus b over 2a. So that'll be minus 480 over 12. So that'll be at negative 40, and I don't know what the value of the parabola would be at that point, but so if we are looking for which y values don't get output, okay, we know that the minimum value, okay, we have to figure out what the minimum value actually is for that parabola. It would be 6 times negative 40 squared plus 480 times negative 40 plus 3456. So that will be negative 6144. Okay, so we know that the smallest that the numerator can be is negative 6144. The x can be anything other than 0. I don't know. I'm not thinking straight. I'm distracted by barking dogs outside. If I have an epiphany, I will come back and share it. If you have an epiphany as you're watching as to how we can prove the range of this function, well, not prove it, but just show algebraically that this is why this function does not output y values between 192 and 768, please do share. Otherwise, catch you another time for another ramble, okay? Ciao. Okay, 3 seconds later, I have had the epiphany I was looking for. Okay, so we are looking for, oopsie, yeah, just to show you that this is literally like 3 seconds after I concluded the video. So we are looking for values of k for which there won't be a solution to this equation, right? So this is a typical nature of roots problem, right? So yeah, okay, so let's put everything over x. So this is 6x squared plus 480x, and then this would be kx over x, right? So the only way that this can be true is if our numerators are the same. So let's get everything onto one side. So 480x minus kx, and then plus 3456. So this is the same as 6x squared plus 480 minus kx plus 3456. Okay, so now we want to look at the discriminant of the equation, which is 480 minus k squared minus 4 times a times c. Right. 480 times 480. So that is 230 of such big numbers, hey? That becomes 960k plus k squared, and then 4 times 6 times 3456 is 82,944. Okay, so 2,000, you guys, 230,400 minus 82,944 is 147,456. Okay, minus 960k plus k squared, right? Just write that more normally. Okay, so this is the discriminant in terms of k, right? Depending on what k we chose over here, Right, so let's look at the relationship as a graph. So it's going to be a parabola, right? So if this is our k and this is our delta, we can figure out the x-intercepts by, well, the k-intercepts using our quadratic formula. Right, so the one x-intercept, well, k-intercept is 768, and the other one is, oh, are we ready to guess? It is 192, right, which is the numbers we were concerned with. Haha, exciting, 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 right? And of course it's a happy parabola, right? So this is the 192, this is the 768, okay? And what we are concerned with is the places where, the places where this doesn't have a real solution, right? Because that will tell us that these values of k are not in the range of the function. The function is incapable of producing these values, right? So we're looking for places where our discriminant is smaller than 0, right? In other words, this is where we're concerned with. These are the k values that don't work for our function, right? So when k is between 192 and 768, the discriminant of our equation is negative, and so the implications are that when k is between 192 and 768, our function does not produce those values, and that indeed confirms this little gap here where our graph doesn't exist. It is incapable of producing y values between 192 and 768. I love algebra. It is an understatement. It's so cool to be able to verify things using different tools, and to find, no matter how you look at the story, it's all telling the same, it's all saying the same thing, it's all sharing the same facts. Anyway, okay, cool. I'm done ranting. Not ranting. What is a happy rant? Rambling. Done rambling. Thank you for tuning in, and especially if you've gotten this far, keep the curiosity alive, and let's convene again and finish off this exam another time.